Here are two things that look totally different. In this bag, I've some soot from the fire. And in this bag, some diamonds. Now, a chemist would say there was a link between these two, despite the difference in appearance. As you may know, diamonds and soot are both different forms of the same chemical element, carbon, and that leads to their having some shared properties. In this program, you'll see that mathematicians, too, are interested in ideas of sameness. So, to start, let's see what's going on over here.
What's the connection between the dance you've just seen and the first 4 non-negative integers? Well, the answer to that question involves groups. So let's start by finding a group associated with the dance. To find a group, you need to break the dance up into individual moves. And to get a better view of those moves, let's look down in the dance. To keep track of what's going on, let's superimpose different colours above each of the 4 couples. And now, let's look at the moves in the dance again. This is the first move. The effect is that all the couples have moved round a quarter turn anti-clockwise. I'll call it A. And this is the second move. The effect is that all the couples have moved round half a turn. I'll call it B. Here's another move. All the couples have moved round a quarter turn clockwise. I'll call this C. And here's the final move in the dance. Couples haven't changed positions at all. This is the identity move, and I'll call it E. So now I've got 4 types of move that happen during the dance. And you can form a group out of these moves by seeing how they combine when you follow one by another.
I'll call this group D. The elements of D are the 4 moves, E, A, B, and C. And the method of combining them, the group operation, circle, is following one by another. To record the composites of moves, I'm going to use a table. It's called a Cayley table, after the 19th century mathematician Arthur Cayley. I'll begin by writing down the 4 elements as the column headings: E, A, B, and C. And then, in the same order, for the row headings. Let's work out one of the entries. Suppose we start with move A and follow it by move B. Now in move A, the couples move round a quarter of a turn anti-clockwise. And we follow that by move B, which is where the couples move round a further half turn. But that's the same effect as a quarter turn clockwise, and that's move C. So I'll enter C in this position in the table. I can find the other entries in the same way, and the completed Cayley table of the group looks like this. Now the question we asked was, what's the mathematical link between the dance and the first 4 non-negative integers? Well, we've made a group out of the dance. Can we make a group out of the integers?
The elements of this group are the integers 0, 1, 2, and 3, and the way that we'll combine them, the group operation, is by a type of addition called modular addition, where you discard multiples of 4. I'll use a Cayley table to record the results of adding the integers. So I'll start by writing the group elements 0, 1, 2, and 3 as the row and column headings for the table. And now I'll fill in one entry. What happens if you take 2 and add on 3 modulo 4? 3 plus 2 equals 5 under the normal rules of addition, and 5 divided by 4 leaves remainder 1. So I can write in the table 3 plus 2 equals 1 modulo 4. And I can fill in the other entries similarly to get this table. This is our second group. Its elements are 0, 1, 2, and 3, combined using addition modulo 4.
We've now got 2 group tables. Here's the group table for the dance. And here's the group table for the integers. What's the link between them? Now, the 2 groups have different elements and different operations, but the elements of each group make a pattern in the body of the Cayley table, and that's something that we can compare. To make the patterns in these 2 tables evident, we're going to colour the elements in the tables. So let's start with the dance group. I'll assign the colour red to the element E, green to A, blue to B, and orange to C. And that gives me this pattern of diagonal lines. Now let's go back to the table of integers. How should we colour this table? Well, if we're going to compare patterns, we need to repeat the order of the colours in the row and column headings. And that means 0 is red, 1 is green, 2 is blue, and 3 is orange. And that gives me this pattern in the completed table. Now you can see the link between these 2 groups. The patterns in their Cayley tables are exactly the same, even though the groups came from totally different situations. These groups both have 4 elements. That is, they're both of order 4. So, do all groups of order 4 have Cayley tables that look like this?
Here's another group of order 4. The elements this time are the integers 1, 2, 3, and 4, and I'm going to combine them by the operation of multiplication modulo 5. That means that you multiply in the usual way, then divide the result by 5 and take the remainder. So let's construct a Cayley table again. For example, what's 4 times 3 modulo 5? Well, 4 times 3 is 12, and 12 divided by 5 leaves remainder 2, so the answer's 2. And the completed Cayley table looks like this. So I can compare the pattern in this table with that in one of the groups you saw earlier, the dance group. let's colour the elements in the table as we did before. We need to keep the same order of colours in the column headings. So 1 is red, 2 is green, 3 is blue, and 4 is orange. And that gives this pattern in the body of the table. This time, the two tables have different patterns. This one has stripes, but this one doesn't. Now, remember, I just wrote down the integers here in the row and column headings in their natural order. But of course, I could write them in any order I like, and that will alter the pattern in the body of the table. So let's look at that more closely. Remember that I'm trying to get a pattern of stripes. Well, this table starts off all right, but this line has both 3 and 4 in it. The 4 comes from 2 times 2, so it's certainly got to be there. But can we do something to get 4s in place of these 3s? Let's see what happens if I swap over the last 2 columns. That means, of course, I've got to swap round the last 2 rows as well. So this is a different way of writing down the Cayley table of this group. Let's compare the pattern in this table with the dance group pattern by colouring the elements here. I must colour the borders in exactly the same way as before. So 1 is red, 2 is green, this time 4 is blue, and 3 is orange. And that gives this pattern in the body of the table. Now the tables do have the same pattern. By rearranging the elements on the borders of this Cayley table, we've shown that it too can have the pattern we saw before. So can all groups of order 4 have this striped pattern if you rearrange their elements? After all, 3 swallows don't make a summer.
Here's one of the symmetry groups that you've met already in the course, the symmetry group of the rectangle. Its elements are the identity symmetry E, rotation through a half turn A, reflection in a vertical line R, and reflection in a horizontal line S. So there are 4 elements, and as in all symmetry groups, the group operation is just composition, following one symmetry by another. And here's the Cayley table for this group. So let's compare this with the dance group that we had before. Are the patterns the same? Well, let's colour the borders of the table as before. E is red, A is green, R is blue, and S is orange. And that gives you this pattern, which is different from the pattern for the dance group. But can you make the patterns the same by rearranging the elements? Well, you can't, because when you rearrange the elements of the table, if you swap 2 rows over, you also have to swap the corresponding columns over. Now the diagonal represents the results of combining each element with itself, E with E, A with A, and so on. So when you swap rows and columns, the elements that were on the diagonal remain on the diagonal. In this table, there are 2 different elements on the diagonal, but in this table, they're all the same. And no matter how you list the elements in the borders of the table, there's no way you can change the elements on the diagonal. So the patterns cannot be made the same. So now we've found 2 distinct patterns for groups of order 4. Are there any others? Here's another group. The elements are the integers 1, 3, 5, and 7, and the group operation is multiplication modulo 8. Here's the completed table. is this a new pattern, or is it just the same as one we've had before? Here's the coloured version of the table. And here's the table of symmetries for the rectangle. And the patterns are exactly the same. So the pattern for this new group is really just one of the patterns that we've met already.
Well, here are the 5 groups that we've looked at so far. The dance group, integers with addition modulo 4, integers with multiplication modulo 5, the symmetry group of the rectangle, and the 4 integers with multiplication modulo 8. And we found that the Cayley tables for these 2 had the same pattern. So they're both examples of the same type of group, which we can represent by a table coloured like this. We say that these groups are isomorphic to each other. That really means that they have the same structure. Similarly, these first 3 are all isomorphic to each other. They're examples of a type of group which can be represented by a table with this pattern. These 2 types of groups have distinct patterns. And in fact, any group of order 4 is isomorphic to one or other of these. So there are really only 2 types of groups of order 4. Well, what about groups of other orders?
Let's look at some groups of order 6. First, the group Z6 of integers 0 to 5 with addition modulo 6. Here are the borders of the Cayley table. And the completed table looks like this. Colouring the elements, this time using 6 colours, gives me these borders and this pattern of stripes. And now, if I remove the symbols, this pattern represents one type of group of order 6. Now, let's look at another group of order 6. In the last group theory program, you saw that the symmetries of an equilateral triangle form a group. Its Cayley table looks like this. Again, I can colour the elements in the table using the same 6 colours as before. And now I can remove the symbols to give me this pattern for a group of order 6. Let's compare this pattern with the one we've already found. Are these patterns the same? Well, not at first glance, but can you rearrange the elements in the borders of this table to make it look the same as this one? Well, you can't. Look at the diagonals. In this table, there's one element that occurs 4 times on the diagonal, but in this table, there isn't. So you can't rearrange the elements to make the patterns the same, and there are at least 2 types of groups of order 6. In fact, any group with 6 elements is isomorphic to one of these. But what properties of 2 groups make the patterns in their Cayley tables the same?
What we want is a definition of the term isomorphic. Precisely what are the conditions for a group G with operation circle and another group H with operation star to be isomorphic? So let's go back to 2 groups of order 4 that we've seen are isomorphic. The dance group D and the group Z4 of integers under addition modulo 4. We coloured the entries in the tables in the same way to show that the patterns were the same. Let's look first at the borders of the 2 tables. For example, we coloured E red in the first table, and we coloured 0 red in the second table. What we've really done is set up a correspondence, a mapping, between E and 0 by colouring them the same way. And we've done the same thing for each of the other elements in the 2 groups. A maps to 1, B maps to 2, and C maps to 3. what we've found is a function mapping elements in the dance group to elements in the integer group. We'll call this function phi. The correspondence between the elements is 1, 1 and onto. And that's the first part of our definition of isomorphic. There must exist a function phi from G to H, which is 1, 1 and onto. But is this sufficient? You see, all this does is ensure that the borders of the tables match up. You also need to ensure that the bodies of the tables match up as well. Let's look again at D and Z4 and think about the patterns in the bodies of the tables. I'll concentrate on one particular position in the two tables, this one. The colour of this entry has to be the same in both tables. In D, the entry in this position is C, which is A circle B. In Z4, the entry is 3, which is 1 plus 2 modulo 4. But remember that we've defined a function phi from D to Z4, so that 1 is just phi of A, and 2 is just phi of B. So we can rewrite the entry in Z4 as phi of A plus phi of B. Now remember that the colours of these corresponding entries are the same in each table. So these entries must correspond under phi. And phi of A circle B must equal phi of A plus phi of B. A simple way of thinking about this relationship between elements is that the image of a composite equals the composite of the images. And this is true for any pair of elements and any isomorphism. And that gives us the second part of our definition of what makes two groups isomorphic. The image of the composite of any two elements must be the same as the composite of the images. And the function phi is given a special name, an isomorphism. We can use isomorphism to classify groups of the same order. The classes we end up with are called isomorphism classes. If two groups are in the same isomorphism class, that means they're isomorphic and the patterns in their Cayley tables can be made the same. But if two groups are in different isomorphism classes, that means they're not isomorphic and the patterns in their Cayley tables can't be made the same. Well, this program has been about groups that are really the same, even though they may look totally different at first sight. And that's the importance of isomorphism in group theory. You don't need to think about every group that exists, just one representative from each isomorphism class.